Imagine a corporate executive high up in a glass corner office somewhere.
Oh, yeah. Probably sweating bullets over a laptop.
Exactly. I mean, they are deeply involved in this massive multi-million-dollar corporate fraud, right? And they're staring at a highly confidential, incredibly incriminating spreadsheet.
The absolute smoking
The
gun.
snuffing gun. So with a trembling finger, they hit delete. But, they don't stop there because they think they're smart. They right-click and they empty the recycle bin.
Ah, the classic move.
Right, and they sit back, wipe their brow, and breathe this huge sigh of relief. They actually think that smoking gun is gone forever. But what if that file isn't gone at all?
I mean, spoiler alert, it usually isn't.
Right. What if it's just hiding in plain sight, completely intact, just waiting for a digital forensic investigator to pull it straight out of the digital ether?
It is, well, it's the ultimate false sense of security. And the reality is, this exact scenario plays out every single day in the corporate world. People just blindly trust the operating system when it tells them a file has been erased.
They really do. So last week, we locked down the physical crime scene, talking about Chapter 5. We talked about tape, physical access, secure perimeters. But today, we have to cross that digital threshold. We're tearing apart the machine itself.
Yes, we are diving into Chapter 6, which covers the exact structure of Microsoft file systems and the Windows Registry.
Which is going to be wild. And if you are studying MIS, CIS, or business right now, especially those of you joining us from the Dr. Sam Pack College of Business at Tarleton State University, managing these enterprise networks is totally in your near future.
Absolutely. And you really need to know that your biggest liability isn't always like some external hacker in a hoodie. Often it's the hidden data sitting right there on your CEO's laptop.
Yeah, that internal threat. Understanding how data is truly stored, hidden, and recovered, well, that's the foundational knowledge you need to protect your organization.
It really is. The best way to secure a system is to understand exactly how it can be dismantled.
Which is exactly why this deep dive is so crucial. But real quick, before we tear into the actual mechanics of data recovery, take a quick second to like, subscribe, and share this with your peers.
Definitely do that.
Because honestly, mastering these concepts is that ultimate insider tip that positions you for a really lucrative future in IT, cybersecurity, or business management. We've also dropped some incredible additional resources in the description below, so make sure to check those out to keep leveling up your skills.
Highly recommend checking those out.
Yeah.
So, should we start dismantling the system?
Let's do it. So if we want to understand how our fraudulent executives, quote unquote, deleted file miraculously survives, we have to start at the physical foundation.
Right.
If we pop the case off a traditional hard drive, what are we actually looking at? And I guess, why does an investigator even care about the physical hardware if the computer just organizes everything into neat little digital folders?
Well, an investigator cares because, honestly, the folders are an illusion.
An illusion?
Yeah.
Like they don't exist?
Not physically, no. A traditional physical disk drive is a really fascinating piece of geometry. It's made up of platters, which are the actual magnetic disks that physically spin around.
Okay, platters. Got it.
Yeah, and hovering just nanometers above them is a head, which is the physical device that reads and writes the magnetic charges. Now, each platter is divided into these concentric circles called tracks.
Like the rings on a tree.
Exactly like that. And when you stack those tracks vertically across multiple platters, you get a cylinder. And finally, each track is chopped up into smaller sections called sectors. Historically, a single sector holds about 512 bytes of data.
Okay, wait. So if I open a regular Word document in Windows, Windows isn't talking directly to the physical head and saying like, hey, go to platter 2, track 4, sector 10.
Not directly, no. I mean, that would be wildly inefficient for the software. The operating system needs a logical map to manage all that raw storage. So it groups a set of those physical sectors together into a logical storage allocation unit called a cluster.
A cluster, okay.
Right. The OS just assigns a logical address to each cluster. So when you save a file, the OS is just looking for the next available logical cluster.
And then before the OS can even start doing that, the drive has to be divided into logical drives, right? Like partitions.
Yes. And the roadmap for those partitions is the master boot record, the MBR. It literally tells the computer, hey, here's where the C drive starts, and here's where it ends.
But that boundary definition, that's where things get heavily exploited, right?
Oh, massively. Because when you format a drive and make those partitions, they don't always sit perfectly flush against each other. They don't always fill the entire physical disk.
Oh, interesting. So there's leftover space.
Exactly. This creates empty spaces called partition gaps. They are literally unused regions between a primary partition and the logical partition.
You know, I'm picturing the blueprints of a house. It's almost like having a void space between the drywall of two adjacent rooms.
That is a perfect way to visualize it. Normally, the operating system entirely ignores that void. It's completely invisible to a standard user who's just browsing their files.
But if someone knows what they're doing,
Right. If a bad actor has administrator privileges and, say, a specialized disk editor tool, they can manually alter the partition tables. They can expand a partition gap and build a totally hidden partition to stash stolen data or malware.
and to anyone opening normal File Explorer, that hidden drive just simply does not exist.
It's invisible. A forensic investigator actually has to use specialized tools that bypass the operating system's logical map entirely. They had to scrape the physical tracks directly to find that hidden data.
Wow, that makes complete sense. I mean, you can't trust the map if the map was drawn by the suspect.
Exactly.
So moving from the physical geometry to how files are actually organized on those visible partitions, Microsoft originally created a database system called the File Allocation Table, right? FAT.
Yes, FAT. And FAT was originally designed decades ago, back when we were literally just trying to organize files on small floppy disks.
Oh, the floppy disk days.
Yeah. But, storage technology evolved super rapidly. We went from FAT12 to FAT16, which hit a massive architectural wall.
Yeah.
I mean, it could only handle disk partitions up to 4 gigabytes.
Right, which is nothing today.
Nothing. So Microsoft developed FAT32 for larger hard drives and eventually XFAT.
Hold on. If XFAT can handle massive drives like up to 128 petabytes, I believe, why do we even need more advanced systems for corporate networks? What's the catch with FAT?
Well, the catch is security and resilience. FAT is fundamentally a very simple index system. It doesn't have built-in file-level encryption, it doesn't journal changes to protect against power failures, and it lacks complex access controls.
Oh, I see.
Yeah. You still see FAT32 and XAT used heavily today on, external USB flash drives and SD cards because they're universally compatible across Windows, Mac, and Linux.
That makes sense.
But you definitely wouldn't run a corporate server on it.
Which brings us to the critical forensic flaw of FAT, which is how it handles deletion. When our executive dragged that spreadsheet to the trash and emptied it, the FAT file system didn't actually overwrite the spreadsheet's data, did it?
No, it didn't touch the data at all. Overwriting data requires the physical movement of the drive head, which takes time and processing power.
Windows wants to be fast.
Exactly. So instead, when a file is deleted in a FAT system, the operating system simply goes to the directory entry for that file, and it changes the very first letter of the file's name to a specific hexadecimal value.
Which is HEXD5, right?
Yes, HEXE5.
So if the file was named like fraud.xlsx, it becomes HEXE5.rod.xlsx?
Basically, yeah. The HEXE5 acts as a giant vacancy sign. It tells the operating system, hey, consider the clusters assigned to this file to be unallocated space.
So it's just available real estate.
Right. It says you are free to write new data over this spot whenever you need to. It frees up the logical space, but the physical magnetic data of the spreadsheet remains entirely untouched on the platters until something else actually physically overwrites it.
Let's put this in everyday terms for everyone listening. It's exactly like tearing the chapter title out of a book's table of contents and then putting a sticky note on the page that says, hey, feel free to write here.
That's spot on.
Because the actual text of the chapter is still completely readable on the page, you just don't have the table of contents pointing you to it anymore.
And that remaining text leads us to an absolute goldmine for investigators, which is drive slack.
Drive slack. Break that down for us.
Well, even before a file is deleted, data can hide in plain sight due to the very nature of how clusters are allocated.
Right, because a cluster is a fixed size. So let's say your system formats a cluster to be 4096 bytes. If you save a tiny text file containing just one single password and it's only 100 bytes long, the file system can't just give it a tiny piece of a cluster.
No, it allocates the entire 4096 byte block to that one tiny file.
Leaving, 3,996 bytes of leftover room?
Exactly. And that leftover room is drive slack.
Yeah.
And it's categorized into two types, file slack and RAM slack.
Okay, file slack first.
So file slack is the unused space at the very end of the cluster. If you previously had a large document saved in that exact spot and you overwrite it with a smaller file, the end of the old document might still be sitting perfectly intact in the file slack.
Just hanging out there. And RAM slack is even wilder.
Right. It is a massive liability.
Yeah.
RAM slack is the space between the end of your active logical file and the end of the physical sector it sits in.
Right.
Historically, older Windows operating systems didn't bother filling that tiny gap with zeros. To save processing time, the OS would just grab whatever random data happened to be sitting in the computer's volatile memory, the RAM, and literally dump it into that physical sector to pad it out to the full 512 bytes.
Wow. If you're a corporate IT director, that should honestly keep you up at night. Think about what sits in RAM.
Everything important.
Unencrypted passwords, domain admin credentials, private decryption keys. All of that incredibly sensitive information could just get randomly stamped into the slack space of a completely unrelated file like a downloaded PDF menu for a local lunch place entirely by accident.
Yes. It creates a permanent hidden record of volatile data. Now, as we transition from external flash drives to the modern data engine, corporate networks running Windows 10, Windows 11, Windows Server, we're dealing with a much more sophisticated architecture.
The NT file system, NTFS.
Right, NTFS.
NTFS was the massive leap forward Microsoft really needed for the enterprise. It brought in the security and access controls that FAT was just missing.
Absolutely. On an NTFS disk, the very first data set is the partition boot sector. And right after that is the absolute beating heart of the system, the master file table, or the MFT.
The MFT, and this isn't just an index, is it?
No, the MFT is a highly detailed relational database. It stores exhaustive metadata about every single file and folder on that partition, and it's incredibly efficient.
Also,
Well, if a file is extremely small, typically under 512 bytes, NTFS doesn't even bother allocating a cluster out on the disk.
yeah.
It just stores the file data directly inside the MFT record itself.
Oh, wow.
Yeah, we call that a resident file.
So the data lives inside the database itself instead of out in the storage yard.
Exactly. And for larger files, non-resident files, the MFT provides the exact cluster coordinates. But for an investigator, the metadata is the real prize.
Because we're talking about creation dates, access rights, system attributes. NTFS acts like an itemized receipt of literally everything that has ever happened on that machine.
It really does. Let's look at specific NTFS system files to see how deep that surveillance goes. Take the UNGL, the Update Sequence Number Journal.
The USN journal.
Right. This is a running, persistent log of actions. It records exactly when data was added to a file, or if a user attempted to cover their tracks by renaming an incriminating document to something innocuous.
Then there is Prefetch. I always find Prefetch fascinating because it perfectly illustrates how a feature designed to help the user actually ends up trapping the criminal.
Oh, absolutely.
Because Windows wants to be fast, right?
Right.
So the first time you run a new application, Windows creates a .pfe prefetch file. It maps out all the specific code libraries the app needs, so the next time you click it, Windows can preload those links into RAM and make the app launch instantly.
The engineering logic is pure performance optimization.
Right.
But the forensic reality is that a prefetch file is a permanent footprint. It records the installation date, the exact timestamps of execution, a counter of how many times the app has been run, and the specific files the application interacted with.
Think about what that does to a suspect's defense in court.
It ruins it.
Completely. If our executive claims they accidentally wiped their hard drive, the prefetch file for their specialized file wiping software will show they didn't just click it once. It will show they launched that specific deletion tool like 14 times over the course of a week.
Exactly. It completely destroys the "it was an accident" defense by mathematically proving calculated intent.
Intent is everything in a corporate investigation. But we also have to acknowledge that NTFS features can be weaponized by the bad guys, too.
Oh, for sure. The perfect example of that is alternate data streams, or ADS.
ADS. How does that work?
Well, this feature was originally engineered simply to give NTFS compatibility with older Macintosh file systems, which used to split files into two parts, a data fork and a resource fork.
Okay.
So ADS allows data to be appended or attached to an existing file without changing the original file's size or its primary function.
Wait. So if I have a normal picture of a cat, ADS means I could attach a secret stolen client database to that image file, and the average user would just see the cat.
Yes. If a security auditor looks at that cat picture in Standard File Explorer, the file size reads normally. If they double-click it, the picture of the cat opens flawlessly.
That is terrifying.
It is. The appended database is completely invisible to the operating system's standard interface.
So how on earth does a forensic tool find it?
By ignoring File Explorer and querying the MFT directly, forensic software parses the raw master file table records. The MFT entry for that cat picture will clearly list multiple data attributes, one for the image and a secondary hidden attribute stream containing the appended database.
Ah, so the MFT exposes the lie immediately.
Exactly. The metadata doesn't lie.
This brings up a critical reality for our future MIS and business leaders listening right now. Data is incredibly persistent, and forensic tools are remarkably good at digging up hidden and deleted files. So how do organizations actually protect their vault?
That's the million-dollar question.
Right, because if an executive's laptop is left in an airport terminal, the company faces massive financial and legal liability if personal identifiable information like PII, social security numbers, leaks out.
Well, a simple Windows login password is not security. I mean, a thief can simply unscrew the bottom of the laptop, pull the physical drive out, plug it into a forensic dock, and read the raw data directly.
Bypassing Windows completely.
Totally. This is why whole disk encryption is absolutely mandatory for any modern enterprise. Microsoft provides a native utility for NTFS drives called BitLocker.
But BitLocker doesn't just rely on software, right? It integrates with the physical hardware of the machine.
Yes, and that's the genius of its design. BitLocker utilizes a TPM, a Trusted Platform Module.
The TPM chip.
Right, this is a dedicated microchip soldered right onto the computer's motherboard. During the pre-boot sequence, the TPM verifies that the hardware hasn't been tampered with, and then it securely releases the decryption keys to unlock the drive.
Meaning, if our airport thief pulls the hard drive out and puts it in a different machine, the drive remains hopelessly scrambled.
Because it's physically separated from the TPM chip that holds the keys.
Precisely. Now, BitLocker is for the entire drive, but NTFS also offers EFS, the encrypting file system, which allows users to encrypt specific individual files or folders. Right?
Yes, EFS operates on a public and private key infrastructure. The public key locks the data, and only the user's unique private key can unlock it.
Okay, if I put my business manager hat on for a second, that sounds incredibly risky.
How so?
Well, what if a disgruntled senior engineer encrypts all the vital source code for a new product, abruptly quits, and deletes their private key? Is the enterprise just locked out of its own intellectual property forever?
That's a valid fear, but Microsoft engineers anticipated the rogue employee threat model.
Yeah.
EFS utilizes an infrastructure that includes recovery certificates.
Oh, thank goodness.
Yeah. When an enterprise domain is configured, the domain administrator account is automatically issued a recovery certificate. It functions as a master skeleton key.
Okay.
So if a user loses their private key or intentionally tries to hold company data hostage, the network administrator can use a recovery certificate to decrypt the files and maintain business continuity.
That is a massive safety net. Now, looking toward the horizon of enterprise storage, we are seeing the rollout of ReefFS, the resilient file system.
Yes, ReefFS Microsoft built this specifically for massive cloud data storage, where data corruption is just entirely unacceptable.
Yep.
ReefFS focuses on maximized data availability and integrity at an incredible scale. And it completely changes the mechanics of how data is saved using a concept called allocate on write.
Allocate on write. How is that different?
Well, in older systems, if you open a document, modify a paragraph, and hit save, the operating system physically overwrites the old clusters with the new data. ReefFS abandons that method entirely.
Because overwriting risks corruption if the power fails mid-save, right?
Exactly.
So instead, when you update a file, ReefFS copies the new, updated data to an entirely new, unallocated location on the drive. Once the write is confirmed successful, it simply updates the directory pointer to look at the new location.
Right. The old data is just left behind, unlinked, but entirely intact.
Wait, if it doesn't overwrite the original data, that is a forensic investigator's absolute dream.
Oh, it really is.
Think about it. If a suspect goes into a financial ledger and alters the numbers to hide their embezzlement, ReefFS's allocate on write feature might naturally preserve the original, unaltered ledger right there on the physical disk, just because the system wrote the fraudulent version to a new sector.
It creates an incredible opportunity for historical data recovery. The system's pursuit of resilience accidentally creates a perfect evidentiary timeline.
That is wild.
But the file systems are really only half the battle. The Windows operating system itself is a massive surveillance apparatus.
If the hard drive is the filing cabinet, the Windows Registry and the system artifact files are the security cameras tracking the user's every move.
Very well put. Let's break down the registry. It looks super intimidating when you open it, but what exactly is it doing?
I mean, I look at the registry editor and I just see a maze of folders and hex codes.
It does look like that.
Yeah.
But fundamentally, the registry is a massive, hierarchically structured database acting as the central nervous system of Windows. It logs hardware configurations, software setups, network connections, and user preferences.
And forensically, Certain sections are way more important than others.
Right, specific sections called hives are crucial. The SAM hive, the Security Account Manager, tracks local user accounts and passwords.
Okay.
The NTFS.dat file tracks the behavior of individual users.
Mhm.
By querying the registry, an investigator can pinpoint the exact user account that was logged in when, say, a USB drive containing stolen data was plugged into the machine.
And the registry is just the tip of the iceberg. The operating system leaves behind digital breadcrumbs everywhere. We call these artifacts.
Yes.
We talked about Prefetch and the MFT, but the hibernation file-hiberfile.sys is arguably one of the most devastating pieces of evidence a suspect can leave behind.
It all comes down to virtual memory management. When you close a Windows laptop lid to go grab a coffee, the computer goes into hibernation to save battery.
Right.
But it needs to remember exactly what you were doing so it can wake up quickly.
Yeah.
To do this, the operating system takes everything currently sitting in volatile memory, your active RAM, and basically freezes it.
Takes a snapshot.
Exactly. It writes that entire block of volatile data directly to the hard drive in a massive file called Hiberfile.sys.
So if we translate that to a practical scenario for an internal investigation, let's say a rogue employee is writing an unencrypted ransom note, or maybe they've used a decryption key to view a stolen database.
Okay, setting the scene.
They are doing this entirely in a temporary memory window. They haven't clicked save. The data exists only in volatile RAM. But then they close their laptop lid to head out for lunch. Did Hiberfile.sys just permanently write their highly volatile unsaved RAM, including the ransom note and the decryption keys, directly to the hard drive?
It absolutely did. The simple, everyday act of closing the laptop lid practically signs their confession.
Wow.
Hiberfile.sys is a frozen snapshot of their active state of mind. Using memory analysis techniques, a forensic investigator can extract that unsaved text right off the hard drive.
That's incredible.
And the same mechanism applies to pagefile.ts. When a computer runs out of physical RAM while juggling too many applications, it uses pagefile.ts as an extension storage area on the hard drive, swapping chunks of active memory in and out.
So it's another avenue where volatile secrets become permanent physical evidence.
Exactly.
And we really can't forget where our executives started their cover-up today. The Recycle.Bin. I mean, it's an icon on the desktop, but behind the scenes, it's a deeply tracked system folder.
Under normal operations, the Recycle.Bin is a safety net. When a user deletes a file, Windows doesn't actually wipe it, obviously. It relocates the data to the hidden Recycle.Bin folder.
Right.
But more importantly, it renames the file and stores the original file path and the exact deletion date in an indexing file, like an info2 file or similar control file, depending on the version of Windows.
And to top it all off, we have internet history files.
Ah, yes.
Every time a suspect browses the web, whether they clear their cache or not, the browser is collecting, transmitting, and often logging that activity deep in hidden directories. For an investigator, pulling internet history isn't just about proving what a suspect did.
No, it provides the crucial missing link in any investigation, the motive.
Exactly. Motive and premeditation. If a server inexplicably crashes and you pull the admin's internet history to find they were heavily researching how to permanently wipe an enterprise RAID array 3 days before the crash, you have established clear intent.
You paint the complete picture of the crime.
We have covered a massive amount of technical ground today. The ultimate takeaway here, especially for those of you stepping into future business leadership and IT roles, is that in the digital world, deleted rarely means destroyed.
Almost never.
Understanding the physical reality of sectors, the logic of clusters, how the registry tracks human behavior, and how system artifacts freeze RAM to a disk. Well, this knowledge empowers you to do two vital things. You can either uncover the absolute truth during an internal investigation, or you can properly secure your own organization's sensitive data with hardware-backed encryption so you never become the victim of a devastating breach.
You cannot defend a system if you do not understand the mechanics of how it stores its secrets.
Think back to that corporate executive from our intro. You know, the one sitting in the glass office, wiping their brow, completely convinced that emptying the trash saved them.
Yeah, that guy.
Thanks to the FAHEX E5 mechanism flagging their data as unallocated space, the Prefetch files logging their wiping tools, and the hidden system files backing up their metadata. They didn't destroy the evidence. They practically gift-wrapped it for the forensic team.
They thought they were cleaning the room, but they were really just leaving a perfect set of fingerprints.
So true. Next week, we are crossing the operating system aisle. We are diving into Chapter 7, covering Linux and Macintosh file systems.
It is a completely different architecture, a whole new world of forensic analysis.
And you definitely won't want to miss it. But before we go, take control of your learning. Explore our channel's other deep dives, playlists, videos, and classes. Continuously learning is how you own your career growth and stay completely irreplaceable in this industry.
And seriously, check the description for those extra resources we've curated just for you.
So I will leave you with this final thought. Knowing what you know now about the permanence of slack space, hidden partition gaps, and the way your temporary RAM sneaks onto your hard drive every single time your laptop hibernates. How secure do you really think your deleted data is right now? That's a wrap on this episode of Digital Forensics. Until next time, analyze the copy, preserve the original.